Right, so drag, chapter 9. We're going to get down to basically one basic formula. And that means that this topic ends up looking really easy, but there are several subtleties to it, and those subtleties are important. Should make you pause and think before you apply the formula. First of all, am I using the correct parameters for that formula? And secondly, what's going on physically? So first of all, a definition of drag, rough one. It's going to be the force of a fluid. Okay, and we talked about lift and drag. So drag is one of those two primary forces of fluids on objects, and it's going to be opposite and parallel to relative motion. I wouldn't stress about this definition too much. The main thing would be, can you apply it to a particular situation and say, oh, okay, yeah, that makes sense. So here we got a box car. We'll get to that later on. Let's imagine that it's going 40 miles per hour. And then it's into a headwind of 20 miles per hour. Okay, so what is the direction of the drag force? Well, hopefully it's pretty obvious to you that the drag force is going to be that way. There's going to be a drag back like that. Okay, but applying that definition opposite the relative motion, well, this box car, you could think about it going 60 miles per hour relative to the ground, okay? And then the drag is going to be opposite to that relative motion. All right, hey, what about a falling object? What about the drag on that? So let's imagine that this is going down, say at 20 feet per second, all right? Well, what direction is the drag? Hopefully your intuition is there's going to be a drag force that's up. But some of you might say, wait a minute, isn't that lift? Isn't that up? Well, once again, it's really, that's really important, that parallel idea. Drag is parallel to the direction of motion. So this is going down, and because of a reaction in the plane of motion or in the direction of motion, there's going to be drag backwards, okay? So lift is going to be up on an object that's going like this. So if we had a force that was up here on like this, that would be a lift force. It is not parallel to relative motion or parallel to motion. It is perpendicular. So there's our first point, understanding what drag is. And then we got to move on to how it is that we're going to calculate drag on a moving object or an object that's moving relative to a fluid. I'm going to start by trying to get a rough feel for how to do drag calculation. So your textbook uses a script T for the drag. Hey, vans are getting pretty boxy these days, or at least some of them, and pretty tall. So let's just take a look at a situation like this. What's the drag going to be there? You might say, wait a minute, in this picture, he has the van, 7 feet wide, 8 feet tall, 12 feet long, stationary. But you could think about it this way. What if there was a 60 mile per hour wind and you were going to push it to try to get this going? Hey, what is the force of the wind on that going to be? And as you push it and get going, it's pretty logical to think about it, or reasonable to think about that as a drag. Okay, so here is the rough statement that is good to keep in mind. We can think of the drag as being equal to the fluid dynamic pressure acting on the frontal area. Okay, where frontal I put in parentheses because area is going to be a big deal, how we figure that out. So if you think about it, pressure in a common unit for pressure is PSI. Maybe we can take the PSI of this wind and multiply it by an area and end up getting the force. And it turns out that that way of thinking about it is very reasonable. So what I'd like you to do is pause the video and see if you can remember what dynamic pressure is. But a quick reminder. We think of a moving fluid as having three types of energy, okay? There is its kinetic energy, okay? There is its pressure energy, and then there is finally its elevation energy. And dynamic pressure is the pressure, essentially the kinetic energy. It's the kinetic energy, the energy of motion. So give that a shot. Okay, so we're gonna go ahead and calculate, but hopefully you've researched, gone back through the textbook or thinking a little bit. The kinetic energy term is 1/2 rho v squared. So we can do that for you here. By the way, I'll just give you the conversion, but 60 miles per hour is 88 feet per second. Why don't you go ahead and do that calculation and get it in pound per foot squared. All right, so I got 9.2 pounds per foot squared. I assumed standard values for the air temperature so that I could go to those basic tables and get the density of air. And then you click through the calculation, you get 9.2 pounds per foot squared. By the way, encourage you to make sure you understand how the units work. Okay, so again, what we're going to imagine is that there's a pressure now associated with this wind, and it acts on an area. Well, what area? Well, the idea then is that it's going to hit this front surface here like this. And so we're going to multiply by what's called the frontal area to get the drag. And so we're going to take this 9.2 pound per foot squared, and we're going to multiply it by a frontal area of 56. So I'm just going to do that quickly on my calculator. Bear with me for just a second. I think I rounded it off a little bit, but approximately I'm going to get the force of drag. Excuse my fingers for a second. So force of drag is equal to 516 pounds. Okay, and so it's going to be really tough for you to stand behind here and push and get this van rolling, in part because there's all that drag force on it. And of course, there's some internal friction, et cetera, and things like that. All right, so there is our first basic calculation. We're not going to write this formula down, but we're going to try to encapsulate the idea, bear with me for just a second, is that roughly what we can do is take the drag and we can do 1/2 rho u squared times the area. Okay, and you're going to see something like that again and again and again. But that is, if we were to write that down, which I hope you didn't, we should put a big question mark behind that. It turns out it works really pretty well for blunt objects where the surface is blunt. Okay, but what if you had some sort of surface that was more streamlined? Okay, and obviously with cars, that's something that we want to do. If we make a surface more streamlined, okay, then we're not going to have that blunt effect there. And what's going to go on in that case? Turns out that this formula has to be modified to be used in more generally. So this you should write down. Here is our most general equation. To get the drag, we're going to take the dynamic pressure energy, 1/2 rho u squared. Okay, we're going to take some sort of area, but this portion of that works pretty well for blunt objects. And we're going to have a modification term, CD, which is called the coefficient of drag. Your textbook and many textbooks present the basic formula that way there. That is a good definition of what the coefficient of drag is. Often if you're doing design, our bottom line is, hey, what is the drag? So you're going to probably do this calculation. All right, so there are subtleties for every single term. Let's go term by term. Let's start with density. What does that stand for? Hey, the density of the object or the density of the fluid? It's the density of the fluid. So make sure that you look those up carefully. All right, what about U? Okay, what about U? Well, it basically is the speed of the object relative to the fluid, speed of the object relative to fluid. So let's take a look at this case right here like this, okay? This is going 40 miles per hour, and you've got a 20-mile-per-hour wind. Well, what we're going to say is that the relative speed is 60 miles per hour. And you'll notice in the textbook, a lot of times they'll draw it again, okay, where they imagine, again, as we said earlier in this, talking about chapter 9, we imagine this being stationary and the wind moving at 60 miles per hour, okay? So they're going to redraw it that way. Mentally, I believe that some of you are going to say, well, look, this is equivalent to the wind, the air being stationary, and this trying to cut through the wind at 60 miles per hour. All those essentially are equivalent. You're going to get the equivalent drag in all three cases. Okay, why don't you quickly get the U in that case right there? All right, the U is going to be 0 because there is no motion of the moving object relative to the surrounding fluid. And so we're going to get U equals 0. So we're going to get no drag in that case. All right, so that is, we've got several terms worked out, rho and U. Okay, what about area? Well, be careful about that. That is a case where you can make a lot of errors, so take a pause. Look at how the area is defined for a particular situation before you do that. And then finally, coefficient of drag. What is that going to be? By the way, it is going to be unitless. You can work that out yourself, but a huge issue is working out the coefficient of drag. And for starters, it's useful before you get the coefficient of drag to have some sense of what is going on with the fluid flow around the object and with pressure drag and shear drag. All right. Pressure drag and shear drag. Essentially what you're going to do is you're going to take your object and you're going to try to visualize the fluid flow around it, and then think of drawing pressure vectors and shear vectors at various points. Finally, you try to put it all together. So let's imagine this is this boxy type van and it's moving to the right at 80 miles per hour. What we could do is we could start by 2 points right here, okay? And I'm going to start with that point there and think about the fluid pressure on it. What direction is the fluid pressure on it? And okay, it's surrounded by air, surrounded by air. So I would draw a vector there like that. The pressure is there like that, okay? And is that going to create drag? Absolutely. And we can work that out. Okay, what about shear? We'll come to that. We'll come to that in just a minute. Okay, how about the top? All right, how about the top? Well, let's start with pressure. Pressure is always normal to the surface, and so it's going to be like that. Is that pressure going to cause drag? The answer is no, okay? Drag is parallel to the direction of motion, and that's perpendicular to the direction of motion. Okay, so what about shear? What if we drew a shear vector at that point? Well, once again, you can think about this object as trying to cut through a fluid, and the fluid's going to act back, the fluid's going to have a backwards force like that on that top surface, and then that's that shear idea. I mean, in a little bit more detail, there's that no slip condition, and then there is adherence between this bit of fluid that's sticking to the top and the fluid above it, and as a consequence of that cohesive force, we get a shear like that. All right, so we have both pressure drag and shear drag. And honestly, pardon me, that is some of the most interesting stuff in Chapter 9 and just in general. How do you actually work out those pressure drags and shear drags, and how do they manifest themselves in different applications? So to get you thinking along those lines, let's just go ahead and do a flat plate facing flow. So that would be like this plate right here, and it's facing some sort of flow. What's the drag going to be on that? Well, there's definitely going to be some drag in that case, but let's try to break it down into pressure drag and shear drag. So let's go ahead and imagine that this speed is relatively low, okay, and we've got a pretty viscous fluid. I use those thoughts here so that we could assume laminar flow. So we're going to assume fairly laminar flow over this object. Okay. Well, we're going to go to some various points on this object and start with pressure. Okay. What if you were to draw a pressure vector at that point like that? Well, clearly the pressure is going to be in here like this. Pressure acts normal. Okay. What if we went to these points on the other side? Downstream of the object, what direction is pressure going to be? It's also going to be in. Test your intuition. Which pressure is going to be bigger on the upstream side or the downstream side? Okay, well, it turns out in a case like this, the pressure is going to be bigger on the upstream side. What we have is this dynamic pressure actually banging against there. And so we get a net pressure force to the right. So that's pressure. All right, let's go to those dots and get shear. Well, to get shear, we have to think about the fluid motion. So hopefully it makes sense to you if this is a laminar case, that this fluid is going to split and go around. So I could just take this vector, this fluid stream, and have it go around here like this. And this bottom, it's going to go around here like this. Okay, but what about the stuff that actually gets close here to this object and say actually comes to close to this point? Okay, well, that is where we get into that chapter 6 stuff where we actually get the streamlines. We had streamline functions, we had velocity potential functions, and you can do this for low Reynolds numbers cases, or for some cases actually, where we can actually get a streamline that goes here like this and then comes around there like that. Okay, in short, if you take a look, if you get really close to the plate, the fluid is actually going to be moving vertically here like this at that point there. And so we're going to get an upward shear at this point like that, okay? The fluid is actually moving down like that. And it's going to be, by symmetry, it's going to be opposite. And the shears are going to end up canceling out. So we're just going to get just pressure drag. Change it to a horizontal plate or a plate that is parallel, its long dimension is parallel to the fluid flow. One thing that I would love to work on more with you guys is, given a verbal description, do the drawing, and maybe we can get a little bit of work on that in the course of this lecture. It is a valued skill. So that would look in this case like I have a plate that is parallel to the flow. And then the question we want to ask is, hey, is there going to be pressure drag there, shear drag, or both? And we're making it a thin plate. We're making it a thin plate. So if you take a look, basically this fluid is going to move over the top here like this. Okay. All right. And so there is going to be shear drag horizontally. What about pressure? Well, if you take a look at the top and the bottom, pressure this way, pressure this way. Okay. And if it's a perfectly symmetrical situation where this plate is aligned exactly parallel to the flow, those two pressures are going to cancel out. We will get some pressure drag, and that will be at that front surface right there like that. But, pardon me, if it's a really thin plate, that's going to be minimal. So this case is a case where we get almost purely shear drag. As a consequence, our equation, which I won't write out, but we had our drag force is equal to the dynamic pressure, 1/2 rho u squared, times the area. And the idea was that dynamic pressure was becoming drag. Doesn't really apply here. And yet, I'll write it out really quickly. Fluid dynamics, people in fluid dynamics, they like to stick with one equation. So as a consequence, this coefficient of drag really needs to get modified in this case, or in general cases where a fluid is, object is somewhat streamlined. All right, so our first case where we're going to try to modify or work with that coefficient of drag is flat plate laminar, which we went over last lecture, quite a few details about flat plate laminar. Why don't you start by doing your drawing, okay? So we're going to jet ski, okay, at 30 miles per hour, okay? Dimensions of our jet ski, 1/4 inch by 6 inch by 4 feet long, and we're going to jet ski on an engine oil. Hey, that's actually just for the sake of the numbers working out in a way that's easy to comprehend. Hopefully you never encounter that in an oil spill and have to do that. All right, do your drawing, do a side view of the jet ski, try to get a feel for what's going on. All right, so a couple things about it. True drawing here, obviously a jet ski's length would be in the direction of motion, so this would be 4 feet. This is a 6-inch wide jet ski, and the 1/4 inch would be the height. It's not very tall, so I'm thinking about this jet ski as moving to the right. Okay, here is a side view of it. Okay, what is going to cause the drag? Well, you know, if you think about, if you idealized a little bit and think of this jet ski as basically on the top of the fluid here that we've discussed, then there's going to be basically no pressure in the front, or just the pressure due to air, which would be pretty minimal. Even if it's sunk down a little bit, okay, in the engine oil, then we would have hardly any pressure drag because there's hardly any area for that pressure to hit. On the other hand, we're definitely going to get shear. Oil is a very viscous surface, and so as we try to, this jet ski tries to move to the right, there's going to be a shear to the left. All right, getting going on some of the math for background. 30 miles per hour is equivalent to 44 feet per second. We know that probably somewhere in this core calculation, we're going to have to do 1/2 rho u squared. So why don't you get that number up there just for background? Okay, so that basic calculation with a little bit of practice, it becomes second nature. I got a huge dynamic pressure, But you got to think about it this way. I mean, imagine that there was engine oil coming at you at 30 miles per hour. That has incredible energy. But this is not going to be converted essentially to pressure force on the frontal area. So we're going to have to approach it in a different way. And this is a kind of an amazing case where theoretical fluid dynamicists were able to work out from first principles what the drag would be. All right, so we actually you can, based on last lecture, you can see how we could get at it. Okay, the drag is due to shear, and we have a formula for getting wall shear. All right, and so what I'd like you to do is pause for a second and get the wall shear just at the end here, just at the end of at the end. So this would stand for the wall shear at 4 feet down. So that would be right there like that. What is that wall shear there? Well, as a reminder, we have a formula and it doesn't always apply. It applies when the flow is laminar. So that would be worth doing as a quick exercise reminder. Why don't you go ahead and get the Reynolds number at the end and then see if you can use the wall shear. And I'll get the numbers up there in just a second. All right, well, here's where I missed being in class because I got people out there doing calculations and checking my work. If I messed up here, I apologize, but the basic equations are right. So to get the Reynolds number along a flat plate, there's our equation. And there's something unique about this particular situation. Usually our length dimension is something overall about the object, like its diameter or its height or something like that. In this case, we get a Reynolds number particular to some sort of location along that plate. And so here, X is the distance from the leading edge. I got 38,940. What's the point of that? That means it's laminar, and that should make sense to you, even though this object is encountering a fluid that's moving fast relative to it. Engine oil has really high viscosity, so it's still going to end up being laminar. All right, the shear formula. If it's laminar, then this shear formula that was derived from first principles applies, and I plugged and chugged, and I got 5.77 pounds per foot squared. Right or wrong, two main points about it. Earlier, the 1/2 rho u squared, we got 1,713, a huge number compared to this number. And so if we were to go just say, hey, we can just use this 1/2 rho u squared, we're going to be way off. Second point about it, how do you interpret these units? This is basically pounds of shearing force per foot squared of surface encountered by the fluid. So what area are we going to end up using in this case? Well, it's the bottom of the jet ski that encounters the engine oil. So it would be the area of the bottom. So that would be 2 square feet. So maybe we can get the drag by doing 5.77 times 2 and getting about 11 pounds of drag. Okay, final point though. This is where understanding of what's going on at a drawing level is very helpful. This formula was for the shear at a particular point. And we thought, okay, well, what actually does the shear look like? We did that last lecture. And so we imagined streamlines going over this here like that. And this could represent the engine oil if you thought about the jet ski moving relative to the engine oil. Okay. And what we end up getting is we get an increasing boundary layer thickness. And we end up getting a decreasing shear the further you go down the plate. And of course, that should make some intuitive sense to you. This first part right here is encountering that engine oil. And we're going to get a tremendous variation in what's going on flow-wise at this point and a lot of shear. Further on, we got less shear going on. And so the classic graph for shear versus X looks like that. Okay, well, what you need to do then, essentially, if you want to get the drag, is you would have to go point by point along here and get the shear and multiply it by the corresponding area. Essentially, you would need to do an area under the curve and an integration. And that is possible to do for this formula, and that has been done. And so a formula that puts it all together has been arrived at, and that's what we'll take a look at next. So the alternative is to go back to the basic equation for drag. And once again, it's helpful to think, okay, there's some sort of fluid dynamic pressure, 1/2 rho u squared, and we're going to multiply it by area, but then we're going to adjust for the particular situation. And if this coefficient of drag is 1, hey, what we basically have is a blunt object facing flow. All right, well, we don't have this in this case. We don't have an object that's blunt and facing flow. So as noted earlier, through an integration, you can see it in the book here was the formula that was developed. So I encourage you to write that one down and be careful to note where it is that applies. Okay, REL. L stands for the length of our object. So this would be the Reynolds number basically at the end. So the procedure on this is first work out your coefficient of drag. Notice that it has a subscript F. Okay, and so we think of there being shear drag or pressure drag, and shear drag is sometimes called friction drag, and that makes sense. We have fluid friction. We have if this object was moving and there was engine oil below, there would be friction that way like that. So this is a frictional drag. Okay, why don't you go ahead and plug in chug, and let's see how this actually ends up working out. Where I think your first step is to come up with this number, and I'll get it up in there in a second so you can check your work. Okay, so the Reynolds number at the end of the plate was 38,940. So I just plugged through the math and I got this number here. And we'd like to be able to interpret it, okay? 1 means a pretty blunt object. Well, this is not very blunt at all, and hopefully that makes some sense. All right, now we want to go ahead and get the numbers right. So some more details on it. We got that, okay? This term right here is 1713, we did that earlier. Okay, what's the area in this case? Well, area can have a variety of meanings. And in this particular case, the relevant area is the area of contact. And in that case, that's going to be the bottom of the ski over here like that. And so that will, we need to be careful about doing that. So let's crank through it and see how the drag actually turns out in this case. Okay, I got 23 pounds. So I just plugged and chugged and put the numbers in there. Again, I really miss being in class to have some of you guys catch any errors that I had. And I'm sorry I don't have the time to do these calculations, 3 or 4 times to make sure I'm absolutely right. But it is a reasonable number. It is important to note that that is on the bottom of the ski. If we were to try to do the complete picture, we would get the drag on the top. Yes, there would be drag on the top. That's the air. And then we would get any sort of pressure drag due to the fact that the ski probably sinks partway into the engine oil. But hopefully you can see that the pressure drag is going to be minimal, and then the viscosity of air is going to be minimal. So in this case, a good beginning calculation would be that's how you're going to get the drag. All right, so that gives you a good feel for it. 1/2 rho u squared. Be careful, and you ought to be able to get that right with too much difficulty. Getting the right coefficient of drag is a challenge, and being careful about area is a challenge. Let's get some more work on coefficient of drag and area. A lot of chapter 9, section 9.3 is how do you figure out the appropriate coefficient of drag for a scenario? A couple things about it. First of all, theoretical approach is great. So the theoretical approach would be that you figure out the pressure drag and the friction drag individually. That has become very challenging to do, so instead we've gone to what's called the empirical or experimental approach, where there's just all sorts of ingenious devices like wind tunnels or even water tunnels or other sorts of situations. And hopefully you guys will get on to ME128 at some point during your time here at Sac State, and you'll get in and use the wind tunnel. And you can actually use the wind tunnel to get coefficients of drag. And that's a very, very interesting topic, and it's neat how it all works out. That is the approach that's usually done, is coefficients of drags are worked out experimentally, and those coefficient drags encompass both friction drag and pressure drag. Okay, it turns out that for many objects, there's not just one coefficient of drag that makes the equation, our basic equation. Let me just write that in there again, CD 1/2 rho u squared A. There's our basic equation. There's not just one coefficient of drag for an object that makes it work. And so what the convention that's come out there is, in some cases, we base the coefficient of drag on the Reynolds number. That might make some sense. The Reynolds number gives a sense of, hey, that flow around our object. How close is it to a turbulent, or is it fully turbulent? And the nature of the flow, of course, hopefully makes some sense to you guys, would determine the nature of the drag. So we determine the Reynolds number, and you got to be careful about how the Reynolds number is calculated, and then go to some sort of chart. So we're going to start with the most basic chart out, the most common one. It's figure 9.23. For the rest of this lecture, I'm going to try to get a chart up there and see if we can actually work out various CDs. So I encourage you to get your book out and flip to those tables. 9.23 in just a couple minutes. Almost there. Bear with me for a second. All right, so here's 9.23. Background idea. Remember, if we had a blunt object, the coefficient of drag would be 1. So that might be a first thing to do, is to get you oriented to this one line. And there's that one line going across there like that. This chart has CDs, coefficient of drags, for two different objects, a smooth sphere and a smooth cylinder. When are you ever going to have a sphere? Well, balls fly through the air, and so many times we need to work out the drag on balls. In addition, compared to, say, something complicated like a sports car, understanding the dynamics, understanding the nature of the shear, the nature of the drag, the nature of the flow around the object is a comprehensible first step is comprehensible for things like spheres and cylinders. All right, well, if you take a look, a good thing to concentrate, I would think, okay, a sphere is not very blunt, so I would think it would be less than 1, but it varies from over 200 to, following the sphere down here, to less than 0.1. There's a huge variation. It's important to note, actually, that we get a range here where it's very close to 0.5, and that might make some sense. Don't go with that. Don't always use 0.5, but it makes some sense that a sphere has some streamline to it, and therefore its coefficient of drag would be less than 1. All right, finally, to actually use this chart, pretty simple. What we do is we decide, are we doing a cylinder or are we doing a sphere? That tells us what curve to use. And we find where we are on the curve by using the Reynolds number. So that would be something to write down, that the Reynolds number for a sphere or a cylinder is rho u d over mu. And you can probably guess what d stands for. That's going to stand for the diameter of the sphere or the diameter of the cylinder. All right, so let's jump in at it. So bottom line for an example like this, we want to work out this term, the drag force. But let me go ahead and read it out loud, and I encourage you to get drawing. I think the drawing's not hard in this case. We've got a 1-foot diameter spherical ball. I forgot the word smooth. We're going to make it smooth, all right? And it is moving horizontally through water, so it's moving through some water at 15 miles per hour, which, by the way, is 22 feet per second. Hey, what's the Reynolds number? What's the coefficient of drag? And what is the drag force? Start by doing a drawing, and while you're doing a drawing, think about what the streamlines might look like. And in addition, should that drag force be large or small? And finally, are we talking about pressure drag, or are we talking about shear drag or friction drag? Get that up there. All right, so here's my drawing. Ordinarily, you might interpret the situation as this ball moving in this direction, say at 22 feet per second, or to the right at 22 feet per second. But you'll notice in the textbook and in most fluid cases, we think of relative fluid motion. So we think of the ball as being stationary, the object being stationary, and the fluid moving relative to the ball. And so that's what I'm trying to show there. All right, what's the fluid going to do? It's going to go around the ball like that. What is the nature of the flow? Is it going to be laminar, layered flow, or is it going to be turbulent? That is an interesting question that we're not going to be able to get to today, but there's some great stuff in the textbook that describes all that. Hey, what is the drag going to be like? Well, 22 feet per second. Imagine that you were at a swimming pool and you saw this 1-foot diameter ball moving through the pool at 22 feet per second. I mean, that is moving. So it should be a pretty significant drag. Last question, is there going to be a pressure drag? Absolutely. That fluid's going to hit this front area right there, and we're going to have pressure drag. But are we going to have shear drag? And the question, and that answer is absolutely as well, because this fluid right here is moving along the surface. And so because of viscosity, there's drag along that fluid. So along that surface. So it's going to be a combination of both. Interesting master's thesis to go ahead and come up with a theoretical derivation of the coefficient of drag by getting the shear drag and the pressure drag and combining them. But the simplified approach is one coefficient of drag that works it out. I would encourage you to get through this. I'll get the answers up there in a second. But note, just a quick note, what about our drag formula? In this case, it's based on the frontal area. Of course, when you do this work, you're going to want to look at the relevant chart or formula and see what area is used in the drag calculation. All right, let's go. All right, trying to be systematic about it. First, I get my Reynolds number, rho v. D in this case stands for the diameter of our object, of our sphere, divided by viscosity. I get a huge number. A lot of times these end up being expressed in exponential notation, so I got 1.82 times 10 to the 6th. Okay, what does that mean, laminar versus turbulent? Well, here's what we have so far. We have pipe flow, where we use 2,100. We have, as a critical number. We have flow along a flat plate, where you use 5 times 10 to the 5th. And I haven't given you a critical number for a sphere yet. Well, for now, don't worry about it. The main thing I want you to note is this is a huge number, okay? And what that's going to end up meaning is we are going to have some turbulent effects in this case. And the second thing it means, it allows us to go to our figure, which is in this case, pardon me, figure 9.23 and get the coefficient of drag. So go ahead and make that your next task. Getting to that figure, almost there. All right, so there is our figure for smooth cylinders and spheres. We are on the solid line. That is the line for a smooth sphere. We are above 10 to the 6th, a little bit above 10 to the 6th. So we need to be over in this area here like that for the smooth sphere. And we can be really precise about it. There actually are curve fitting equations. Let's just be rough and get it for right now. Somewhere about 0.25. Somewhere about 0.25. You may quibble with that. That's what I'm going to go with. The main point that I want to have is this less than 1. And that's because a sphere is not a very blunt object. That's a great way of thinking about it. Why is there this dip down here? That is very, very interesting. We'll maybe get into that a little bit later on. But let's go with 0.25. All right, so we got our estimate of the coefficient of drag is 0.25. We're going for it. All right, so putting it all together, to get the drag, to get our drag, we want the coefficient of drag, we want that velocity pressure, okay, or dynamic pressure, and then we want the frontal area. So dynamic pressure, I got 470 pounds per foot squared. Wow, well, it's moving fast and it is a dense fluid, so there is going to be a lot of dynamic pressure. How about the area? This case, it's the frontal area. So what you want to do is you will want to, when you get frontal area, you're going to want to imagine that you're looking at the object from the front and see what dimensions you would perceive. This case, it's really, really simple. If I were looking at this from the front, I would see essentially a circle of diameter 1 foot. So pi d squared is going to be pi over 4. Let's crank through that and combine it and see what we get for the drag. Okay, putting the numbers together, I've got 93 pounds of drag. If this object, what would the result be? Well, if this object were, for example, moving through some sort of stream like this, then it would decelerate very, very quickly because that would be the only horizontal force on it and slow it down. So there's a first calculation where we go through the whole process. We end up having our basic formula and we work out the different parameters in order to plug and chug and get out a drag force. So if you flip through chapter 9, the end of chapter 9, the drag section, section 9.3, you're going to see all sorts of tables for CDs. And with a little care, they're easy to use, but I want to emphasize a little care and hopefully some understanding thinking about the nature of the flow. So let's take a look at an ellipse. There's well worked out numbers for that. And an ellipse might be our starting point towards working on an airfoil or an airplane wing. So the numbers, the way it's presented in the table is we have an ellipse with a certain distance here, which is not diameter actually, so you want to be careful. And then it has a certain length along the other axis parallel to the flow. And of course, then we need some sort of length along here to define our ellipsoid or however, pardon me, our elliptical shape. From a two-dimensional point, it looks like this with here is our a cross section of our ellipse and the flow going around there. Okay, well, that's very difficult to do theoretically, so it's summarized in the figure. What I want you to do is go to figure 9.20 and get oriented, and then let's go ahead and fill out this chart. And the first case we're going to do is let me get it up there, is L over D is approximately equal to 0. What's that ellipse going to look like? And again, working yourself on going from some sort of verbal description or otherwise geometrical description to getting a drawing yourself is a great skill. So why don't we pause, get that figure 9.20 and get what this ellipse cross section is going to look like, and finally get the CD. Almost to 9.20. Bear with me for just a second. All right, good challenge using this, this diagram, or this figure 9.20. You'll see that there are two curves, and so the question becomes what curve to use. Here's one way of thinking about it. The x-axis is the ratio of L over D. That's helpful. Secondly, the solid curve tells us that if L over D is 0, which is the particular case we're looking at, we get a flat plate normal to the flow. So that would mean the surface of our plate is perpendicular to the flow. Well, let's go back then and look at the first example and see what the appearance would be. So taking a look at this case here where L over D equals 0, okay, that would mean basically that this L should be a very, very small number. So just imagine it just being just a quarter inch or something like that. Well, what's this ellipse going to look like? It's basically going to look like a flat plate because L is very small and D is a certain distance. So it's basically going to look like a flat plate. And we've got this flow coming here like this. And so we have a flat plate that's normal to the flow. So what we can do then is we can actually, for these examples that we're going to do, is use that solid curve. And that's what we're going to do. So back to the curve. Almost there. Bear with me for just a second. Okay, so key line is 1.0. If it's 1.0, that's kind of like a landmark for us. So if it's a flat plate normal to flow, we get a CD of 1.7. And that means that we're going to get a lot of drag. And of course, a flat plate, we should get a fair amount of drag. So let's so one thing, I'll get that up there in just a second for you. The coefficient of drag is 1.7 in this case. Okay, what area are we talking about then? Okay, well, if you work your way down, the area is going to be B times D. There's the coefficient of drag defined for this term, and the area is B times D. Okay, let me get back to the whiteboard. Bear with me for just a second. Okay, so there's the information I've got. I've got the coefficient of drag is 1.7. The area is BD. So B actually is how long it is, and D is how tall it is. And of course, that would mean then that BD in this particular case is the frontal area of the plate. It would be the area you see if you look directly at the plate. Okay, bear with me for a second. Let's get the second example up there. Okay, let's see if L over D equals 1. First of all, what is the appearance going to look like? Let's not go ahead and go to the figure yet. Let's go ahead and get the appearance. So go ahead and pause for a second and think about, well, what if L over D is equal to 1? What is that going to actually look like? All right, well, you should get the cross section as a circle, because if L over D are the same, then we have a circular area. And the shape of this object now basically is a cylinder. We've got a cylinder. We could go back to the previous figure that we used. Let's see if we can get that information from the figure 9.20 that we were just using. So bear with me for a second while I get back to that figure. Okay, so what we want to do is we have L over D equal 1, and we want to use the right curve. So you're reading up there, and if L over D is equal to 1, okay, I'm right there, I get a CD of 1.0. Notice the other curve is 1.0 as well, so this is a case where it doesn't matter what curve we actually end up using. Finally, what area are we going to use? Again, we're going to end up using area BD. And then we can take off and do our pressure drag calculations. Sorry, just need to correct something I just said. I said we could do our pressure drag calculations. This would be combined. In this case, the C that we're using, the CD we're using, 1.7 here versus 1 here, is going to actually get us the drag calculation total. Finally, what area we would use? Well, again, as in many cases, we end up using the frontal area. So you want to imagine that you're looking at the front of this object, and if you looked at the front of this object, you'd see a dimension this way, which was B, and you would see a height, which is D. So you would see this area BD, and so the area that we would use in our calculation would once again be equal to BD, and that will be everything we need to do to get our drag calculation. On that ellipse-shaped example, some of you might have said, hey, what about the Reynolds number? We'll take a look back at that figure. And this is very, very typical for what you see if you do this drag type work. So going back to that figure, looking at the graph, there's no Reynolds number in there. But notice that they actually, there's no Reynolds number on the x-axis or on the curve. But up here, they specify the Reynolds number, and they say that this works if the Reynolds number is about 100,000, which is maybe not an atypical value for things that are close to a plane wing, etc. So something to be careful about. What Reynolds number does the chart or graph apply to? So notice that the examples we've done so far, like a cylinder and a sphere, they've been smooth. Or the flat plate, it was smooth also. Okay, what if it's rough? Does it make a difference? Absolutely. I mean, if you think about something like a golf ball, that surface is not smooth. And that's a lot of manufacturing effort to get all those dimples in there. What difference does that actually make? Once again, theoretically, it would be really, really tough to work out. So the people have done tons of testing in wind tunnels, etc., and come up with values. So let's go ahead and go to the table for that. Hang in there for just a second with me. This is figure 9.27. So take a second and get to that table in your book, and I'll be pulling it up. All right, so there's 9.27. Great googly moogly. Initially, it looks pretty complicated, but it's really not that bad. So let's find the smooth curve and also take a look at what the x-axis is. So the x-axis is our Reynolds number. The y-axis is our coefficient of drag, which would be our basic formula for drag rearranged, solve for the coefficient of drag. There's that 1/2 rho u squared term, and that is the frontal area of a sphere. If you were looking at the sphere from the front, what area would you see? And you would see pi d squared over 4. Okay, hey, let's find the smooth on there. So there is the smooth curve, which reflects exactly what we saw earlier. If you went back to that smooth curve, it would be very, very identical. It has that really pronounced dip at some point, okay? And then we have our relative roughness, which is exactly the same calculation as our pipe. It's how rough the surface is relative to the diameter. What difference does roughness make? Okay, well, I'm going to get to this fairly large roughness line right here, 1.25 times 10 to the negative second. Okay, well, if you take a look, say at this number right here, 1,000,000 for the Reynolds number, the coefficient of drag is much larger if it's rough. Okay, what about the golf ball? Well, if we think about taking that golf ball, all right, and if we look at Reynolds numbers that are corresponding to a golf ball through flight, interestingly enough, even though it's rough, it has a lower coefficient drag than the smooth. And once again, that's a pretty fascinating topic. The book does a good job of discussing it. For right now, our goal is just going to be able to pick out the right coefficient of drag, think a little bit about the nature of the flow, and then do the calculation correctly. All right, let's finish it off with a really practical example, and this very quickly gets pretty practical. So let's say we're doing some parachute design. We're going to make life easy. We're going to go with a nice, easy number. We're going to go with a 20-foot diameter parachute. And let's say, how's that going to work out? Are we going to get sufficient drag when it gets up to 8 feet per second? I mean, and visualize that. Would you want to hit the ground in 8 feet per second? That's like going from the ceiling of your house, ceiling of your room, to the floor in 1 second. We don't want to go a lot faster than that. Okay, well, the first thing to do is to get a drawing to represent the situation. Go ahead. All right, well, I've made some progress, okay? My parachute, pretty crude, but I'm visualizing it as essentially the outline of it is half a sphere. Okay, it's going down at 8 feet per second. But remember, in most cases, the book is going to imagine our object being stationary and our fluid moving towards it. Okay, we're trying to figure out the drag. There's our basic formula, but when someone might say, wait a minute, there's no drag here, that's lift, that's an upward force. But once again, drag is a force parallel to the motion. The motion is up, and so the drag is going to be up. Okay, good. Oh, by the way, it can be in the same direction as the motion of the fluid or opposite the direction of the motion of the object. So that's the drag. Okay, so we need to go through and do this calculation. 1/2 rho u squared is not going to be that difficult. CD, we got to find an appropriate source within chapter 9. And then area, hopefully if we read carefully, it will tell us what area to do. So for starters, let's take a look at figure 9.4 and see if that's going to do the job for us. Figure 9.4. Looking for figure 9.4, bear with me for just a second. Okay, there it is. So I'm going to take a minute to get oriented. It has some Reynolds numbers drag coefficient. Got a circular disc? No, parachute's not a circular disc. Not this type either. Sphere? No, parachute's not a sphere. What about a hemisphere? That's looking pretty good. If you take a look at that parachute, we could maybe think about it as a hemisphere. Area, pi d squared over 4. That's the area we would see. That's the frontal area. If we were looking up at the parachute from below, looking up from the parachute below. Okay, but what about this here? It says it's for low Reynolds numbers. This is for low Reynolds numbers. So the Reynolds number is going to be rho u d over mu. Is that going to be small? Well, let's go through it piece by piece. Density. Air's density is very low. So that looks good. U, 8 feet per second. Diameter, 20 feet. Not that big. All this stuff is looking not that big. But what about viscosity? And air's viscosity is very, very small. So we are going to get a huge Reynolds number. 9.4 doesn't apply. What you would do then is, flip through your various sources. Of course, you could look online or get some sort of guidance and try to find a figure or table. And the next one to look at is 9.31. So let's go ahead and take a look at 9.31 and see how that works out. Going to 9.31. All right, there we go. So they've got a bunch of different figures in there, pretty interesting stuff. Why don't we decide between the first two? Which would be better in our case? And what would the coefficient of drag be? Does it even apply? All right, well, I got two choices here, a solid hemisphere or a hollow hemisphere. Clearly, the hollow hemisphere would be the better choice because a parachute's hollow. How about the reference area? Pi d squared over 4. That's making a lot of sense. That would be the frontal area, the area we would see if we were looking up at the parachute. Okay, which drag coefficient applies, all right? Well, these arrows indicate the flow, the direction that the air is flowing towards our object. And the first one is if the air is flowing like that. And if you think about it, if the parachute's descending like that, the flow would be that way like that. So we would choose 1.42. The other one's much lower if the air is actually coming and going around this small surface, 1.42. Hey, can we use it? Is our Reynolds number greater than 10 to the 4th? It is. So that is a great choice. thing about it is, before we actually move on and use that 1.42, is there are actual coefficients of drags worked out for particular objects, and not just shapes, but particular objects. So let's finish off class by looking at 9.32 and see how that calculation works out. So let's see, I think I have 9.32 is the next one. So there's 9.32, and they've got some pretty interesting objects in there. They have a dolphin, they have a tree, they have tractor trailer trucks with a coefficient of drag about 1 if it's really, really blunt. But if you put that little fairing or gap seal there, you can really bring down the coefficient of the drag. The same thing with biking, about 1 if you're upright, but get down low and you get a much lower coefficient of drag. They also give you the areas, which is kind of interesting. So for biking, things are pretty well worked out. Flags, etc. This may all look like, wow, who took the time to do it? It turns out economically, there's all sorts of design decisions made on drag numbers, and we need some good way to do it. So it's worth working it all out. And there we go. We got the parachute in there. So the coefficient of drag is 1.4. You might say, hey, over what Reynolds numbers? Essentially what you can assume in this chart is that the given coefficient of drag applies for the normal speeds at which something would actually be moving. So let's use that 1.4 and go ahead and finish off this example that we're working on. So getting that back up there to remind you, okay? We got the parachute, 8 feet per second. We're gonna go term by term and work it out. I got CD of 1.4. Let's see if we can finish it off. Well, I got not good enough. Back to the drawing board. Let's see how the numbers turned out. So the first thing is that dynamic pressure energy number, 1/2 rho u squared. And it's a small number. And why is that? Well, the density of air is very, very low. On the other hand, our area is good, 300 square feet, the essentially cross-sectional area at the bottom of this parachute. Okay, and then putting it together, there's our CD, there is our 1/2 rho u squared, and there's our area, and I got 33.5 pounds. Doesn't sound bad, but it's truly not good enough if you think about it. If we did a diagram of what's going on, okay, there's our parachute, roughly. Okay, and there's our person descending at 8 feet per second, going down at 8 feet per second. Okay, what we have is we have a drag force up, okay, of about 33 pounds. And then we have this person's weight down. And let's just make them a 160-pound person or whatever. Okay, what's going to happen in that case? Well, clearly there's more weight down than drag up. You're going to speed up. Well, the drag is going to increase, and that's good, but we don't want to speed up more than 8 feet per second. So you could get back to design and think about what you need to do. And one possibility is to make the diameter of this parachute bigger so that at a reasonable speed we get a greater drag. All right, that does it for this lecture. I encourage you to get going on homework number 9. I will be adding answers to it, and I will be corresponding more with you guys about getting through test 2 this week and how to take it and some steps for success. So talk soon. Take care, guys.